Hello everyone, good evening. So welcome to the session 14 of ray optics. So in this session, right, we'll continue with our discussion on the microscope. So we already in the previous session, right, we talked about the microscope, simple microscope, compound microscope. We basically looked at all the formulae corresponding to them, right? In this session, what we'll do is we'll take a look at the formulae once again and we'll go through some sample problems. And then we'll continue into the telescope part. Okay, so we'll start. So for the simple microscope, right, when we have the microscope in the normal adjustment or the relaxed view, so I'm just going through the formula that we already covered in the previous session. The magnification, right, see here magnification is in terms of what? In terms of the visual angle. Magnification is in terms of the visual angle. Okay, so the relaxed view will be what? When the final image is formed at the infinity, that is when our eye will be able to see it in a relaxed. This is also called as what? Normal adjustment. For that, what is the magnification? D by f. Okay, now the other arrangement is when we keep the object such that the final image is formed at the near point. The final image is basically formed at the near point. That is the arrangement, right? So here what we'll have, the magnification will be higher. So magnification in this case will be what? 1 plus d by f. Magnification will be higher, but the trade-off is what? Here you will have to strain our eye to see the final image. That is the thing. Okay, so this is about the using of the simple microscope. And remember, simple microscope, what we said, the focal length value should be small. Why? Because we can see that in the magnification formula, focal length is coming in the denominator, right? If the focal length is small, means we can have a higher magnification, but the spherical, aberrations or the chromatic aberrations, right, will mean that we will not be able to really achieve higher magnification values with the simple microscope, because we'll start getting some aberrations. And to avoid it, we'll take a combination of two lenses. So one lens which will keep close to the object, that is called as objective. Other is the eyepiece. So again, the arrangement, right, is kept in such a way that we will be able to form the final image which will be inverted with respect to the original object. The final image can be formed at infinity, that is the relaxed view. In this case, what is the magnification? VO by UO. So VO is the distance from that objective to the first image formed. First image will be acting as the object for the eyepiece. VO by UO. UO is the distance of the object from the objective into D by FE. The length of the microscope is basically the distance between the objective and the eyepiece. You can see here it is what? The general formula will be what? VO plus UE. But relaxed view means final image should be formed at infinity, right? Means UE will be equal to what? FE. UE will be equal to FE. So thereby the length of the microscope becomes what? VO plus FE. Okay. So this is about the relaxed view of the compound microscope. And the other way is the final image formed at the near point. The final image is formed at the near point D. So here obviously we will get a higher magnification. You can see the same change will come. VO by UO into 1 plus D by FE will come. Okay. And the length of the microscope will be what? VO plus, this is the UE value. What is the UE value? D into FE by D plus FE. Okay, so this is coming for the condition that you are using. What is the condition? The image for the eyepiece, right? The image is formed at the near point. That is the condition we are using. Okay, so the length of the microscope in this case is what? VO plus D into FE by D plus FE. You can see the magnification is what? It is higher than the relaxed view or the normal adjustment mode. but again the trade-off is what you'll have to strain your eye a little bit. So on this, right, when we are expecting questions means we will usually get questions straight formula type, like whatever the formulas we are seeing, right, we will be getting questions straight on the formulae. So we'll just have to make sure that we are thorough with the formulae, and because these kind of questions, when they're coming in the final examination, right, we should actually take advantage of it, in the sense we should solve them in a lesser amount of time, so that we will be able to use this whatever the buffer time that you're saving for the other problems. Okay guys, so we'll just get into some questions. Let us see. So look at this question, guys. It's a straightforward question. A simple microscope has magnifying power 3. We're talking about a simple microscope. When the image is formed at the near point, I think I might have told you, near point, we can remember it as 25 centimeters, otherwise they will give us also. Okay. Simple microscope has a magnifying power. That M is what we are referring to as the magnifying power. Magnifying power is what? 3. The image, final image is formed at the near point of a normal eye. We need to find what is the focal length. We have to find what is the focal length of that. See, what is a simple microscope means? It is just a converging lens, right? Simple microscope means what? Just one converging lens. That is what is simple microscope, correct? Now tell me what is the answer for this. So what is the formula? In case the final image is formed at the near point, what is the magnification formula? 1 plus d by f, right? For a simple microscope. So this is given as what? 3. They are giving us magnifying power is what? 3, right? So 1 plus 25 centimeter by f. Okay. So we'll take the 1 to the left side. 3 minus 1 will be 2. 2 is equal to 25 centimeter by f, which means what? F will be 25 by 2 centimeter. Check it up guys, what is the answer? So that's it. If you are able to remember the formula means, we will be able to, not only in the case of the simple microscope, but also compound microscope also, right? You'll see, even if you are practicing questions, Lakshmi, good, okay, even if you are practicing some questions, right, you'll see that the questions will be coming straight on the formula type. Okay. So there is not much to think over here guys. Whatever the we need to make sure that for these optical instruments, right, we have to thoroughly make sure that all the formulae we are comfortable. Okay, so Arun, good. All the formulae we should be comfortable, and it will be just like, you will have to go and substitute. The only thing is, if you go through the derivations, then you will be comfortable in terms of remembering the final formula. Okay. So let us go to the next part. So the next question is about the compound microscope. Look at this guys, this is about what? Compound microscope. Compound microscope consists of objective lens, focal length 2 centimeter, and eyepiece. See here, I want you to observe one thing. Generally, right, the focal length values will be small for both of them. In case of the compound microscope, focal length value will be small for both of them, but in between them, right, the objective will have a lesser focal length than the eyepiece. But broadly, what is it? Both the focal length will be smaller value, but in between them we will generally have what? Objective having a lesser focal length than the eyepiece. Okay, you can see in this question, objective, what is the focal length? 2 centimeter. Eyepiece will be what? 6.25 centimeter. Separated by a distance of 15 centimeter. What is this means? This is the length of the L, right? This is the length of the microscope. When they say that no, the two are separated by 15 centimeter means that is the length of the microscope. How far from the objective should an object be placed in order to obtain the final image at least distance of distinct vision? The near point can be also called as what? Near point can be also called as what? The least distance of distinct vision. So basically this is the compound microscope. Final image has to be formed at the near point. And in this they are also asking what is the magnifying power. So guys, we have talked about this compound microscope. The final image has to be formed at where? It has to be formed at the near point. The final image has to be formed at the near point, right? So what are the relations we have? We have the magnifying power formula as well as the length. We have the magnifying power formula as well as the length, right? So look at this. What is the given information we have? The information we have is the objective length, focal length is 2. So FO is 2 centimeter. Eyepiece, what is it? 6.25 centimeter. Okay, so we can also write it like what? 25 by 4 centimeter. 6.25 means what? 25 by 4. Just in case we don't want to have a decimal, right? We want to have integer or fractions, means we can write it as what? 25 by 4 centimeter. Okay. Now L is given 15 centimeter. D we know 25 centimeter. See, from this length of the compound microscope formula, right, we can find VO. See what they're asking us to find: how far from the objective should an object be placed in order to have the final image at the near point. Means they're asking UO value. See, if you are able to, from this formula, right, from this formula let us get the VO. If you get VO means FO is there, you get VO means you can use the length equation. For the objective we can use the length equation. So look at this, guys. First we'll use this length of the microscope formula. So L is what? 15 centimeter is equal to VO plus D is what? 25. Okay, into FE. FE is what? 25 by 4. Divide by D plus FE means 25 plus 25 by 4. So look at this now. This is what? If you take an LCM means denominator will become what? 25 into 4 is what? 100. So denominator becomes 125 by 4. 4 is cancelled. 25 ones, 25 fives. So what we'll have is 15 centimeter is equal to VO plus 5 centimeter. Means VO will be 10 centimeter. First, using the length formula we are able to get the VO. Using the length formula we are able to get the VO, right? Now what is the next step? Once we get the VO, as I said, right, we will go to the objective. We'll go to the objective and use the which one? The length equation. What is the length equation? 1 by VO minus of, because we have to take it as a negative, right? What is the length equation? 1 by V minus 1 by U is equal to 1 by F, right? So here the object distance is measured to the left side. That is why we are putting minus UO. Okay. So 1 by UO is equal to what? 1 by FO minus 1 by VO. What is FO here? 2 centimeter. So 1 by 2 centimeter minus 1 by VO is what? 10 centimeter. So what is this we'll have? We will have it like, how much it is? 5 minus 1 by 10 centimeter. That is 4 by 10 centimeter. That is 1 by UO. Means UO will be what? 10 centimeter by 4, that is 2.5 centimeter. So we have to keep the object where? 2.5 centimeter from the objective. See, these questions, as I said, right, they will be based upon the formula. No need to think much as to how we'll get it, because at the end of the day, what is it? You have combination of lenses and we are talking about the image formation because of that. That's it. But already we have derived the result and we will use the formula. That's so what we have here is the UO value is coming. That is the first part of the question, right? Check it up, guys. We must get the UO as what? UO should be coming as what? 2.5 centimeter. That is the first part. Second part of the question is what? They are also asking us What is the magnifying power? What is the magnifying power formula? Look at this. VO is what? 10 centimeter by UO is what? 2.5 centimeter into 1 plus D divided by FE. FE is what? 6.25. So 6.25 force 2.51 2. So what we have is 4 into 1 plus 4, that is like what? 4 into 5, that will be 20. So we'll call this microscope as what? 20x. The magnifying power is coming as what? 20, right? So we'll call the microscope as what? 20x. Remember that notation I told you in the previous class? So depending upon the magnifying power, right, we will use this word. Okay. So clear, guys? This is about, so we just have to remember the formula and we can solve questions based on the microscope, whether it is a simple microscope or the compound microscope. Okay. Next, look at this one. In a compound microscope, focal lengths of the two lenses 1.5, 6.25 means this will be what? Already I told you, comparatively the objective will have a lesser value. So FO will be what? 1.5. FE will be what? 6.25. If an object is placed at 2 centimeter from the objective, this is UO. Final image is formed at 25 centimeter from the eye lens, means what? This is the near point condition. The near point. The distance between the two lenses is, means they are asking us the length of the compound microscope. This is what? Same. Previous question also same concept, right? But the question model is different. But it's the same. Compound microscope, final image is formed at the near point. So in this question, what they're asking us this L. The length of the compound microscope. Distance between the two lenses is what? That is the length of the microscope, right? Distance between the two lenses is what? That is the length of the microscope. This is the length of the microscope. Okay. Now see what we need to find out here. Let us see what is given. D is given to us. Okay. F. So in this formula, we have to focus on this formula, right? FE is given to us. What is FE? 6.25 centimeter. If we know VO means that's it. So we should know VO. How do we get VO? We will go to the objective. For the objective, we will apply the lens equation. For the objective, we will apply the lens equation. Means what? 1 by VO minus 1 by, where we are keeping it? 2 centimeter, right? Is equal to 1 by FO. What is FO? 1.5. Okay. So 1 by VO is equal to what? This will go to the right side. We should keep a minus over there. Why minus? Because 1 by V minus 1 by U, right? U should be taken as a negative. The U should be taken as what? Negative. So minus of minus, this becomes plus. So 1 by 1.5 minus 1 by 2. What is this? 1 by 1.5 minus 1 by 2 will come. Solving this, we will get the VO value. Check it, what will be the VO? 1 by VO is equal to 1 by 1.5 means what? This is 2 by 3 minus 1 by 2. Okay, that's like what? 4 minus 3 by 6, that is 1 by 6. So VO will be 6 centimeter. So VO is 6 centimeter. So we have to calculate the length, right? Length of the microscope, which is what? VO 6 centimeter plus D into FE. D is what? 25. FE is what? 6.25 means already we did this, right? 25 by 4, like that we can write. Divide by D plus FE. So denominator will be what? 125 by 4. So here 4 is cancelled. 25 ones, 25 5s. 5 ones, 5 5s. So what we'll have is the length of the microscope will be 6 centimeter plus 5 centimeter. That will be what? 11 centimeter. What will be the answer? 6 plus 5, that will be what? 11 centimeter. Check it up, guys. What will be the answer we should get? We should get it as what? Option D. We should be getting it as what? Option D. Okay. See, all these formulae, as I said, right, you will have to, because obviously, you will not be able to straight away remember the formula like that. You will have to make sure that you solve at least couple of problems on each and every formula, so that you will familiar with the use of the formula. That is what will help you in easily remembering it. Okay. So, but the question that we can expect in the JEE mains level or the NEET level from this microscopes will be straight on the formulae. Okay, so JEE advanced, I mean, we do rarely get questions on this, but mostly in JEE advanced we will get questions on the combination of lenses, image formation by the combination, like we have 2-3 lenses together, maybe one of them could be silvered, like combination of lenses with some modifications, right? They might ask us to find the image characteristics, etc. But that will not be straight away like a microscope kind of question, because microscope is what it is, a combination of, compound microscope is a combination of 2 lenses, right, which are arranged in a particular manner. That's it. So for that we have got some derived results, and mostly in the mains or the NEET level we'll have questions straight coming on the formula type. Okay, now the microscope, right, will have something called as the resolving power. What is it called as? Resolving power. So this is an area where we can again sometimes get straightforward either formula type questions, especially NEET. We have got the resolving power of microscope and resolving power of telescope. So in fact the 2020 NEET also we got a question on the resolving power. So what is this resolving power? We will be able to understand more about this when we go to the wave optics part, but here we will try to look at it like a result. If you look at microscope, right, what is the main purpose of microscope? We are trying to see the small objects, nearby objects only, but very small. Okay, if you look at the minimum distance between 2 lines, like you have lines, there is a distance between them, right? Let us look at what is the minimum value of the distance. What is the minimum value of the distance? Okay, so this distance between the 2 lines, we are looking at the minimum value, and we are observing it by using what? Microscope. We are observing it by using the microscope. Okay, so the minimum distance between the 2 lines at which we can see them distinctly, because if you bring the lines even closer means the microscope will not be able to give us the distinct images. The microscope will not be able to give us the distinct images. So we are looking at considering very thin lines or whatever it is, which are having that minimum separation, that minimum value of this distance between them, right, for which the microscope can give us the distinct image. This minimum distance is what we call as the resolving limit. Generally we will represent this by the notation RL. Understand what will be a better microscope, because if this distance between the 2 lines is even smaller, if you are able to clearly give the distinct images, right, that is what is a better microscope. So we'll talk about the resolving power as the reciprocal of this resolving limit. So resolving power is going to be an indication, because when we want to choose a microscope, right, for certain very precision based experiments, we want to have a microscope which is having a high resolving power. So the resolving power is nothing but what? Reciprocal of this resolving limit. What is resolving limit? Think about it. You have 2 closest lines. If you bring them even more closer means the microscope will not give you distinct images. That minimum distance between those lines for which you will get the distinct images is called as what? The resolving limit. And we want to have, when we talk about the resolving power, it will be defined as the reciprocal of the resolving limit. So we have a formula for the resolving limit. Resolving limit will depend upon the wavelength of the light that is used for seeing the particular object, lambda, and the mu value. What is this mu? Mu is the refractive index of the medium between the object and the objective. Here mu is what? Refractive index of the medium between the object and the objective. Okay. And the formula is what? Lambda by 2 mu sin theta. So when we go to the wave optics, we'll talk about how we'll be able to understand this resolving limit using the concept of the wave optics. But here we'll just take it like a result. Okay. So what is it? Lambda by 2 mu sin theta. Here the angle theta, right, is actually called as half cone angle. What is the angle theta called as? Half cone angle. Half cone angle means here you have an object. The radius, the lens will have an aperture, right? The radius of that. Because full aperture means what? Diameter. Full aperture means what? Diameter, right? We look at the angle surrounded by one radius, that is by half cone angle. You see it like a cone, right? Full cone you can see. Object is here, and the objective will have a circular boundary, right? It will be having a circular boundary. If you think of it, it will be like a cone. Half cone angle is what is theta. The angle formed by the radius of that lens at the object. That is what we call as the half cone angle. Okay. So the resolving power will be what? It will be reciprocal of the resolving limit. It will be what? 2 mu sin theta by lambda. What is it? It will be 2 mu sin theta by lambda. So here the thing is we need to understand the relation between the resolving power, mu value, theta and lambda. So what is the relation? Resolving power is inversely proportional to lambda. Resolving power, right, is inversely proportional to lambda, which means what? If you use a colored light of lesser wavelength, the resolving power will be more. Means what? If you use violet will have a lesser wavelength, so resolving power for the violet will be higher. Red, resolving power will be less. Okay, so this is about the resolving power of the microscope, which will be helpful in choosing, because for high precision uses, right, of the microscope, we need to have higher value for the resolving power. So here we look at the resolving power more like a result, and we will be able to get some more clarity on the resolving power when we go to the wave optics part. Okay. Now the other thing is, when we talked about the compound microscope, right, we have been mentioning about the characteristics of these two lenses. One is the objective, second is the eyepiece. So the objective and eyepiece, both of them should have smaller focal length values. Means what? The setup of the compound microscope, right? What is a suitable arrangement for creating an compound microscope which will give us a large magnification value? The FO value and FE should be small. So why it should be small? Because you look at the magnification factor in the normal adjustment. The magnifying power in the normal adjustment. We'll just take one formula and try to analyze. The normal adjustment, what is the formula? VO by UO into D by FE, right? So here you can see FE is coming in the denominator. If FE is less, means magnifying power will be what? Higher. If FE is less, means what? Magnifying power will be what? Higher. And look at this, no, VO by UO. We will go to the objective and then apply the lens equation. What is the lens equation? 1 by VO minus 1 by minus UO, because UO will measure to the left side, that is why negative. VO will be positive, is equal to 1 by FO. Okay, so this will be what? Plus. Now what we'll do is we'll multiply both sides with VO. So VO by VO plus VO by UO is equal to VO by FO. So this is 1. From here what we'll get, VO by UO is equal to what? VO by FO plus 1. So again you can see here what is happening. The FO is coming in the denominator. FO is coming in the denominator. Okay. So if FO is less, then what is going to happen? This VO by UO will be what? Higher. That's what we want, right? So we want to have the overall magnifying power should be what? Higher. And for that, the focal length of the objective as well as the eyepiece should be smaller. That is one. The second thing is the objective, right, which is what we are keeping close to the. So here we have a microscope is for what? For seeing the small objects, right? Here we have a small object. We want to keep the objective very close to the object that is there, which means we need to have an aperture which will be small enough so that we will not be able to have aberrations. Because if you have a larger aperture, means what is going to happen? We will be having aberrations, because here the object is a very, very small object, and the light rays emerging from the object will be coming through a very small area. So we will be requiring just lens with a smaller aperture so that we can avoid the aberrations. Okay, so here the setup for having a compound microscope is what? We will be requiring to have a smaller focal length for both the objective as well as eyepiece, because that will give us higher magnifying power. Comparatively between them, right, we will have the objective having smaller. Between the objective and eyepiece also, object will have a smaller. Okay, and the aperture of the objective, right, will be small, because the actual object is small object. So we just require a small lens there, small aperture lens, so that we can see the light rays coming from the object comprehensively. Because when we require a large aperture, if you want to capture more amount of light rays coming from the object, that we'll see when we go to the telescope, the object will be at infinity. So you want to capture more amount of light rays, means we need to have a larger aperture. Otherwise the image formation will be dull. But here we will not have that issue. Okay, so we will have small aperture so that we can avoid the aberrations. Okay, so this is about the setup of the compound microscope and how it will actually help us in achieving some specific conditions. Okay, now look at this imagery. I don't know if you or somebody who is interested in astrophysics, etc., probably you might have come across this imagery. These are all very famous imagery taken from the Hubble telescope. Okay, so Hubble telescope, right, is a kind of a different one. Why? Because this is not on the surface of the earth. It is actually launched into orbit around the earth. So what happens is, for the normal telescopes which we use to see the other solar systems or other planets, etc., we'll have the issues with regard to the clouds or the atmospheric layers, etc., because the light rays, when they go through the atmospheric layers, right, they do undergo refraction, because the atmospheric layers, they have different optical properties, because of which, right, there can be some issues in terms of what we observe might not be giving us a complete clear picture. So the space telescopes, right, so Hubble is an example of a space telescope. Okay, so space telescopes, they will be launched into an orbit, usually an orbit around the earth, and they will not have these issue with regard to the clouds hindering the observations, or the other effects of the layers of the atmosphere. So this was launched into the Earth's orbit in 1990, and this has really helped a lot of astrophysics. The data that is coming from the Hubble telescope, right, people do analyze it and trying to understand, some phenomena happening in the universe, etc. Okay. Now our goal here is to understand how these telescopes will actually work. So what we'll begin with is the astronomical telescope. So we'll try to focus on mainly two telescopes. One is what we call as an astronomical telescope. Second will be the terrestrial telescope. Okay. So just like the microscope, the way we have seen compound microscope, astronomical telescope also will have two lenses. It will have what? Two convex lenses. And what is the purpose of this? The purpose of this, not only the astronomical telescope but other telescopes also, right? What is the main purpose of them? To provide angular magnification for the distant object. The object is here very distant. We will have to take it like what? Infinity. The image formation should provide angular magnification. And here we will have the objective. So this is what objective and this is the eyepiece. But compared to the microscope, right, we'll have a difference here. Here the objective will have a larger focal length and much larger aperture than the eyepiece. Understand this. The FO value will be very high in comparison to FE. And the aperture of this, aperture means what? If you think of it like a circular boundary, the lens, the diameter or whatever you call it, that represents what? Aperture. Aperture of the object will be large. Why? I will tell you. Why we need a larger aperture objective? Because here the light rays are coming from long distance, right? So you want to capture as many light rays as possible so that the image formation will be bright enough. If you take a small aperture, means what happens? The number of light rays that will come in will be from a small area. The image formation will be dull. We want to have a brighter image formation, means what? We should have a larger aperture. Remember the difference between the compound microscope and astronomical telescope? Compound microscope, objective, we took a small aperture because there it's a micro object. We don't require a larger aperture. But here we take a larger aperture for the objective because we want to allow more number of light rays to come in so that the image formation will be bright. And why focal length of the objective should be very high in comparison to the focal length of the eyepiece? That we will be able to understand once we discuss about the outcomes of the astronomical telescope. Okay. So here the final image, right, can be formed either at the near point, just like the way we talked about in the compound microscope, either at the near point D or at the infinity. So we'll again call it like near point means that is the constrained view, strained view. Infinity means it is the relaxed view or normal adjustment. Same language. Okay. So here you will see that the result will be similar. The formulas we get right, formulas will be similar. The only thing will be what? The comparison in terms of the lens properties. Like you can see here, as I said, the objective will have a higher focal length and larger aperture. There it is not the case. So we will just look at how the astronomical telescope will actually work. So look at this one. This is what we have as the astronomical telescope. Here, right, the original angle, the visual angle. Remember, in case of the compound microscope, what we used to say? We used to use this word theta naught, like that, right? We used to use the word theta naught. What is theta naught? It is whatever is the height of that object divided by d. We will keep the object at the near point. But here the object is not in our control. Object is already sitting at infinity. Object is already sitting at the infinity. So what is this original angle that we take? The original angle that we take is the angle that will be formed by the object at the objective lens, alpha. So you can see here, this is alpha. The final angle formed by the image is beta. The final angle will be formed with respect to eyepiece. So the magnification here, right? The magnification here we will take it as modulus of beta by alpha. So look at this. Why we take a modulus, you know, because already the final image is, we can say, inverted. The final image is inverted with respect to original object. In astronomical telescope, final image will be inverted with respect to original object. Okay. So look at this alpha value. What is, again same, tan alpha will be what? This A dash B dash by FO. So that we'll take it as, for small angles, tan alpha will be taken as what? Close to alpha. Okay. Then what is tan beta? What is tan beta? A dash B dash by UE. Means we'll take beta as what? A dash B dash by UE. So look at this. We will do mod beta by alpha, right? So which is what? A dash B dash by UE divided by A dash B dash by FO. So what we'll get? FO by UE. What is the magnification? FO by UE. Okay. So magnification will be what? FO by UE. So here the original angle means this is not like our theta naught in case of the normal object which is close to us, because when you have object in our control, right, we'll say the maximum possible visual angle is what? When we keep the object at the near point, like that. But here it is not the case. We have to measure the magnification with respect to what is the original angle formed. Original angle formed is what? Alpha. So the magnification is what? Mod beta by alpha. Why are we putting modulus? Because we already know that the overall magnification will be inverted. The overall magnification will be what? Inverted. Okay. Now the length of the telescope. So length of the telescope, same thing. The distance between the objective and the eyepiece. What is it? FO plus UE. So what is the magnification? FO by UE. That is the magnification. And what is the length of the telescope? It is what? FO plus UE. So here we look at the first condition. What is it? Relaxed view. What is relaxed view means? We should have the final image formed at infinity. It is not D, it is formed at what? Infinity. Correct. So if it is formed at infinity means this UE should be equal to what? FE, right? Because the I1 image formed by the objective should coincide with the focal point 1 of the eyepiece. Then the final image will be at infinity. Just look at this. If final image is infinity means UE must be equal to what? FE. UE should be equal to what? FE. That's it. So what will be the formula? If UE is equal to FE, what we will get? The corresponding magnification is what? FO by FE. What is the corresponding magnification? The final image formed at infinity, FO by FE. What is the length of the astronomical telescope? FO plus FE. And remember what we talked about? The focal length comparison, we said what? The FO value should be very, very high in comparison to FE. Now you can understand. Look at this magnification. If you have FO very, very high in comparison to FE, right, what we are going to get? The magnifying power value will be high. The magnifying power value will be what? High. So this is about the magnifying power for the astronomical telescope. In which arrangement? It is the relaxed view. Now just like that, we also discuss about the constrained view. What is constrained view means? The final image is formed at D. Constrained view means what? Final image is formed at D. So look at this. What we will do? We will use the lens equation. We will use the lens equation at eyepiece. Okay. What is it? V is equal to minus D. U is equal to minus UE. F is equal to what? FE. So use the equation. 1 by V minus 1 by U is equal to 1 by F. So minus minus becomes plus. So from here what we have is 1 by UE is equal to 1 by D plus 1 by FE. So from here, right, if you take an LCM, means it is what? D into FE by D plus FE, that is 1 by UE, means UE will be what? D plus FE by D into FE. This is the result. So what is the UE value? If you are forming the final image at the near point, means we are going for the lens equation of the eyepiece. From there, what we get? The UE value we are getting. What is the UE value? UE value is what? D plus FE by D into FE. Okay. So now what we'll do? We'll just substitute this. We'll just have to substitute this. Okay. So look at it, what we have. UE is what? What is the UE value? We have D into FE by D plus FE. This is it, right? Now look at the length of the astronomical telescope. FO plus UE, right? In place of UE, what we'll keep? In place of UE, what we'll keep? D into FE by D plus FE. What about the magnification? FO by UE means it is what? FO divided by UE is what? D into FE by D plus FE. So this will go to the numerator. Okay, so what is it? Magnification is what? FO into D plus FE by D into FE. So what is it? If you keep FO by FE outside, take the D inside, what will get? 1 plus FE by D. So what is the formula? FO by FE into 1 plus FE by D. So this is what is the magnification. So we are having what? The formula for the magnification and the length of the astronomical telescope in the constrained view. So just like the way we have seen in the case of the compound microscope, right? We are looking at the results in the case of the astronomical telescope. Okay. Now the thing is, in case of the astronomical telescope, as you've seen, the final image is what? The final image is always inverted. So the magnifying power, we are taking the modulus value, but we should know that the actual magnifying power is what? Negative, because the final image is what? Inverted, right? If the original angle is formed is up above the principal axis, final angle formed is below the principal axis. It will be inverted. Okay. Now the abnormality in terms of the magnification, it's getting inverted, right, can be corrected by using a small modification, and that is what we will be referring to as the terrestrial telescope. So what is this small modification? Just we will be introducing an erecting lens. How we'll introduce the erecting lens? See, already we have an objective, we have eyepiece, everything. So terrestrial telescope, everything is as it is, like the way we have in the, as it is, as we have seen in the astronomical telescope. We have the objective, large focal length, large aperture, eyepiece, comparatively small focal length, small aperture, everything is same. Now the I1 image by the object is formed at some point. This will be now inverted because I1 is inverted, right? I1 is inverted. So when the image formation is happening because of the objective, that is forming an inverted image. This inversion is corrected. That's why we call this middle lens that we are keeping as what? Erecting lens. So erecting lens will be set up like this. The I1 will be at 2f. If f is the focal length of the erecting lens, I1 will be formed at what? 2f. And this I1 is now the object for this erecting lens, right? It will form an image I2. So remember, if you are having an object at exactly 2f for a convex lens, image will be what? 2f distance on the other side. Image will be 2f distance on the other side. But it will be what? Inverted with respect to the object, means here the a dash b dash is down, so a double dash b double dash will be what? Up, so it is corrected. Now this I2 will act as the object for the eyepiece. This I2 will act as the object for the eyepiece. So we need to understand the difference between the two. So look at it. So here AB is forming a dash b dash inverted. Straight away our eyepiece is giving us what? Our eyepiece is giving us inverted, overall final inverted. But here we are just making some small modification. We are introducing an erecting lens. The I1 will be at 2f from the erecting lens. So it will form an image I2 exactly 2f. It will form an image I2 exactly 2f. Now no magnification is happening because of erecting lens. It is just giving a reverse image. That's it. It is not doing any magnification as such. So you know what happens? Remember the general magnification formula we talked about. What is it? M is equal to what? FO by UE. This is the formula, right? This is the general formula we talked about for the astronomical telescope. That will be as it is. Only the thing that will change is the length. Length of the telescope will change. Why it will change? Because look at it. This is what? FO. This is UE. For the normal astronomical telescope, what is the length of the telescope? FO plus UE. But here it will be what? 2f and 2f. Totally 4f will come extra. That's it. So whatever the results we have, right? With regard to the magnification, they will be as it is. The astronomical telescope results and the terrestrial telescope results, magnification wise, they will be as it is. The change will come when we are talking about the length of the telescope. Length of the telescope will be what? Whatever the length you have in the astronomical telescope plus 4f will come. What is the f? F is the, what is this f? F is the focal length of the erecting lens. The only thing that we need to remember is what? This terrestrial telescope will now give, see here magnification formula, as I said, we are taking the modulus. This magnification taking the modulus, right? For a normal astronomical telescope, we should be keeping in back of our mind that the magnification, overall magnification is actually negative. The final image is inverted with respect to original object. But the terrestrial telescope, right, it will be giving us the erect image. Final image will be what? Erect. Okay, so magnifying power will be what? In this case, positive. Now, whatever the results we talked in the case of the astronomical telescope, right? Remember, magnification is what? FO by FE. When we are forming the final image at infinity. When the final image is the near point, FO by FE into 1 plus FE by D. Already we have done this. Astronomical telescope. Same formulas will be as it is. Magnification, nothing is going to change. Only thing that will change is what? Length of the telescope. Look at this. In case of the astronomical telescope, when the image is formed at infinity, right, length of the telescope is FO plus FE. FO is what? Objective length focal, and FE is what? Eyepiece focal length. We will get plus 4f. Similarly, when the final image is formed at the near point, in case of the astronomical telescope, you know what we had? We had FO plus D into FE by D plus FE. Here we will get plus 4f. Only thing is what? In the length of the telescope, plus 4f will come. That's it. And it is giving us what? What is the purpose it is solving? It is giving the final image as erect, so that when we are observing things, right, we will not have any issues in terms of the inverted image. Okay, so this is about the terrestrial telescope. And when we look at the working of the telescope, right, one of the important things, just like the way we talked about the resolving limit and resolving power in case of the microscope, here also we talk about the resolving limit and resolving power of the telescope. So what is this resolving limit and resolving power? Look at this. The smallest angular separation between two distant objects whose images can be seen separated. That is what we call as the resolving limit. Means what we have, so here when we talk about the object that we'll observe by using telescope, means the object will be distant. The angular separation, so here we have the telescope, the angular separation between them, right? This is d theta, small angular separation. What is the smallest angular separation? The objects are very distant, they are very far away. What is the smallest angular separation between the objects which can form distinct images in the telescope? That is what we call as the resolving limit. And obviously, if you want to have a better telescope, right, what is it that we want to achieve? We want to make sure that this d theta is as minimum as possible, correct? We want to achieve the resolving limit to be as minimum as possible. And the resolving limit, right, d theta value for the telescope is 1.22 lambda by a. So here again we will be able to get some more clarity about this when we go to the wave optics, but here we look at it like a result. What is this? This is the question, I think it has come in the NEET 2020 paper. What is the resolving limit of an telescope? It is what? 1.22 lambda by a. Lambda is what? The wavelength of the light that is used for illuminating. A is the aperture of the objective. So the lens, right, objective lens is there. Aperture means what? We can take it like a diameter. It represents what? Diameter. A represents the diameter of the objective lens. Okay. And the reciprocal of the resolving limit is basically what we call as the resolving power. So the definitions of resolving limit and resolving power, they will be synonymous in both the microscope and telescope. The resolving power will be what? 1 by resolving limit. So which is what? A by 1.22 lambda. Here also we can see resolving power, right, is inversely related to lambda. In the case of the microscope also we saw the same thing, right? Resolving power will be inversely related to the what? The wavelength. Means what? Here violet will have a high resolving power. Red will have a low resolving power, like that. Okay, so this is about the resolving power of the telescope. And here one thing that we can quickly look at is if you want to have a high resolving power, see the aperture of the objective should be what? High, for high resolving power. So already we gave one reason why we should have a high aperture for the objective. One is what? So that you can capture more number of light rays coming and the image formation will be what? More bright. That is one. Second thing is what? If we have a larger aperture for the objective, we will be able to have a high resolving power. And see, if you keep on increasing the aperture, means what? If you look at the lens like this, right, the circular face of the lens, that size, you call it as a diameter, right? So if you keep on increasing the aperture, means what is going to happen? You know, the size of the lens will be increasing. And as the size of the lens increases, we are going to get the aberrations. Not only that, it will cause problems in terms of, you know, the setting up of the entire telescope. And it will even cause, issues in terms of the easy movement of the telescope. So when you are having, you know, a higher aperture lens, that will be able to give us a high resolving power. But the issues with that is what? It will cause one, aberrations. Second is, you know, the lens will become so huge and the entire telescope will become very heavy. And in fact, no, the largest objective lens that we have is actually a lens of 40-inch diameter. Because if you go beyond that, means what we will be seeing is generally aberrations will come. The moment aberrations come, right, like chromatic aberrations or, you know, the spherical aberrations, the image formation will not be proper. Then there is no point in using that particular telescope. So we will be using the telescope only with very less or minimal aberrations. Okay, so where is this, you know, largest lens objective? It's at the Wisconsin. So you can see the diagram also for this. You know, this is the Yerkes Observatory. So what is the diameter of this 1.02 meters. Now, in order to avoid these issues, because if you are having the lenses used in the telescopes, right, we are having the issue in terms of aberrations coming in, and then the size of the telescope becoming very large. There is an alternative approach to design a telescope, and that is by using the mirrors. Instead of using the lenses, right, we can design a telescope by using mirror. So what is this telescope that are designed by using mirror? They are generally called as reflecting telescopes. What do we call them as? We'll call them as what? Reflecting telescopes. And one such reflecting telescope is this Cassegrain telescope. So basically it will use two mirrors. The Cassegrain will be using two mirrors. Okay. So first, the objective mirror. Here you will not have a lens. We'll have what? Mirror. The advantage with this is mirrors are not heavy. Mirrors will be light. So entire design of the telescope will be very light. We can adjust it. We can move it from one place to one place easily. And the mirrors will not have the aberrations, chromatic aberrations. They will not be there in the case of the mirrors. So we'll have the objective mirror. In case of the Cassegrain, we'll have two mirrors and eyepiece. Objective mirror will reflect the rays coming from the distant object, whether it is a distant planet or whatever it is we are trying to observe. Then the secondary mirror, right, will focus these rays through the eyepiece. The secondary mirror will focus these rays through the eyepiece. Sometimes we can even have some reflecting telescopes with just one mirror and eyepiece, because the Cassegrain telescope, right, it will give some flexibility in terms of where the eyepiece can be kept. Otherwise, right, if you are having just only one mirror and one eyepiece, right, we should keep the eyepiece at the focal point, because the parallel rays will be focusing on the focal point of the mirror, right. So we should be fixing the eyepiece at one point. But if you are having two reflecting mirrors, means it will give us flexibility in terms of where we keep the eyepiece. Okay, and it will be not causing a lot of issue in terms of the heaviness of the telescope. Why? Because mirrors after all will be light only. So even if you have two mirrors, the entire setup will be still not that heavy. Okay, so the Cassegrain telescope will use what? Two reflecting mirrors. One is the objective mirror, other one is the secondary mirror. Rays from secondary mirror will go through the eyepiece, and here we will have our eye for making the observation. Here we'll have the observer who will make the observation. Okay, so this is about the reflecting telescopes, which will remove some of the disadvantages. What are the disadvantages with the normal lens based telescopes? One, it will give chromatic aberrations. Second, they will be heavy. So the mirror based telescope, reflecting telescopes, they will be light and they will not have the aberrations. You can see we have one in India near Kavalur in Tamil Nadu itself. Okay, so this the diameter, the objective mirror diameter is what? 2.34, and this is set up. You can see it's a reflecting. So you'll have the design, right? You'll have basically two mirrors. Okay, so we have two mirrors, and also we have the largest reflecting telescope in Hawaii, USA. So they actually a set of two of them. You can see how large they are. So the entire setup, right, is kept inside these dome like structures, but you can see this is like a building, right, and it looks so small in comparison to the entire setup. So the reflecting telescopes, right, they are basically having advantages over the normal lens based telescope, because they will not have these aberrations, and they will be light in terms of moving from one place to other place. Okay, so this is about the optical instruments, and with this we have completed the ray optics and optical instruments, and we will have to discuss about the optical phenomena, like optical phenomena around us. Some of the examples, right, like why the stars will be twinkling, and why we see color of the sky to be blue. Some of the optical phenomena around us, we'll make a separate video on that, and then in the next session, right, we'll proceed into the wave optics part. Okay, we'll see in the next class.